Hello, in this lecture we will find the radius of the small circle. In the drawing we have a quarter circle and we know that chord CD equals to 2 units, and we also know that angle BCD is a right angle. It equals to 90 degrees, and we also know that OD, line segment OD, equals to 3 units, and inside the quarter circle we have small circle, and we want to find out the radius of this small circle. Okay, so first of all we will define the center of the small circle as point P, and then we will join together points A and P by a straight line. Actually, line segment AP is the radius of the small circle because of the fact that it starts from the center of the small circle, that is to say from point P, and ends at point A, that is a point on the small circle itself. Therefore, AP is the radius of the small circle. So we will call it R, small r, and we will also join points P and B together by a straight line. And we will define the touching point between line segment CB and the small circle as X. X is the touching point between line segment CB and the small circle. Then we will join points P and X together by a straight line. Actually, PX is also the radius of the small circle, because line segment PX starts from the center of the small circle and ends at point X, that is a point on the small circle itself. Therefore, PX is the radius of the small circle. And we will define angle ABP as theta. Okay, so this angle is defined as theta, and actually tangent theta equals to AP over AB. Again, tangent theta equals to AP over AB, and we know that AP is the radius of the small circle, so tangent theta equals to AP, that is small r, the radius of the semicircle, over AB. And if we multiply this equality by AB, we will get that the radius of the small circle equals to AB times tangent theta. Okay, so actually, in order to find out the radius of the small circle, we have to find out the value of AB and the value of tangent theta, and then we will multiply AB by tangent theta, and this will be the radius of the small circle. So first of all, we will find out the value of tangent theta and then the value of AB. Okay, so actually I will draw triangles ABP, and the triangle PBX again. Okay, so here we will have triangle ABP. This is triangle ABP, and I will draw also triangle PXB. So I draw again triangles ABP and triangle PBX. So I will prove that those two triangles can congruent to each other. Okay, first of all, we know that AP equals to PX, AP equals to PX, and both those two line segments are the radiuses of the small circle, therefore they are equal to each other. So AP in triangle ABP equals to PX in triangle PBX. Then we know that PB equals to PB. PB is a common side. It actually belongs to triangle ABP, and PB also belongs to triangle PBX. So PB equals to PB, it is a common side. And also AB of triangle ABP equals to BX of triangle PBX, and those two sides are equal to each other according to two tangents theorem. Okay, so two tangents theorem states that two tangents theorem states that the lengths of two tangents from common external point to the circle are equal. So I will read two tangents theorem again. Two tangents theorem states that the lengths of two tangents from common external point to the circle are equal. The lengths of two tangents from common external point to the circle are equal. So actually this theorem says that if from external point of a circle, that is to say from point B, you draw two tangents to the circle, tangent BA and tangent BX, then those two tangents are equal to each other. That is to say AB equals to BX. Okay, AB equals to BX. So actually we proved that all the sides of triangle ABP are equal to all the sides of triangle PBX. Therefore, triangle ABP is congruent to triangle PBX according to side rule. I will read again the things that I wrote. Triangle ABP is congruent to triangle PBX according to side rule. Actually, side rule means that if you prove that all the sides of one triangle congruent to all the sides of another triangle, then those two triangles are congruent to each other according to side rule. Okay, so we proved that those two triangles are congruent to each other. Therefore, from the fact that those two triangles congruent to each other, we can conclude that angle ABP that equals to theta, angle ABP, this angle is equal to angle PBX that will be also equal to theta. Okay, this angle PBX also equals to theta, and those two angles are equal to each other according to the rule that corresponding angles incongruent triangles are equal to each other. Again, angle ABP equals to angle PBX according to the rule that corresponding angles in congruent triangles are equal to each other. Triangle ABP is congruent to triangle PBX, therefore the corresponding angles, angle ABP and angle PBX, that are corresponding angles, are equal also to each other. So both those two angles are equal to theta. Okay? So in the next step, we will extend CB and DO until they intersect. Okay? Until they intersect, and the intersection point will be defined as point E. Okay, so here point E is the intersection point between DO and CB after we extended it. Okay, actually we have here angle, actually this angle, angle EBO, and angles ABC are two vertex angles. Again, angles EBO, this angle, angle EBO, and angle ABC are two vertex angles, and therefore they are equal to each other. Okay, angle EBO is equal to angle ABC according to the rule that vertex angles are equal to each other. Vertex angles are equal to each other. Again, I will remind you what is vertex angles. Actually, if two lines intersect each other, they create two pairs of vertex angles. We have here angle 2 and angle 4. Angle 2 and 4 are vertex angles, therefore they are equal to each other. And also we have the second pair of vertex angles, that are angles 1 and 3, that are also equal to each other. Okay, so here in the drawing we have two vertex angles, that is to say angle EBO and angle EBC are two vertex angles, and therefore they are equal to each other. So what is the size of angle ABC? Angle ABC equals to theta plus theta, that is to say it equals to theta. So angle EBO that is equal to angle ABC will be also equal to 2 theta. Okay? again angle EBO, this angle equals to angle ABC, and both those two angles are equal to 2 theta. Okay, and from the fact that we have here a quarter circle, we can conclude that DO is the radius of the quarter circle, and also we can conclude from it that angle DOB is a right angle, that is to say it equals to 90 degrees. Okay? And actually it is given us in the question that angle BCD equals to 90 degrees. And the angle BCD is a vertex angle. Angle BCD is a peripheral angle. Again, angle BCD is a peripheral angle because it is inside the quarter circle, and we also know that angle BCD equals to 90 degrees. Okay, angle BCD equals to 90 degrees. Angle BCD equals to 90 degrees, and it is a peripheral angle. And we have a rule that any peripheral angle that equals to 90 degrees must rest on the diameter of the circle. So I will read the rule again. The rule states that any peripheral angle that equals to 90 degrees must rest on the diameter of the circle. So actually we know that angle BCD is a peripheral angle, and therefore, according to the rule that I stated, we know that angle BCD is a peripheral angle that equals to 90 degrees. Therefore, according to the rule that I stated, angle BCD rests on the diameter of the circle, that is to say DE is the diameter of the quarter circle. So we can derive from the rule that because of the fact that angle BCD is a peripheral angle that equals to 90 degrees, the peripheral angle BCD rests on the diameter of the quarter circle, that is to say, angle BCD rests on the diameter of the quarter circle that is to say, DE is the diameter of the quarter circle. Okay, DE is the diameter of the quarter circle. Okay, we know that the diameter of any circle equals to 2 times the radius of the circle, and we know that DO equals to R, so the rest must be also equal to R in order to complete the size of DE to 2R. So if DO equals to R, then OE must be also equal to R, because DE is the diameter of the quarter circle, and DE therefore must be equal to 2R. So if DO is R, then the rest of DE, that is OE, must be also equal to R in order to complete the size of DE to the diameter, that is to say, in order that DE will be equal to R, OE must be equal to R, because we know that DO equal to R. Okay, again, DE is the diameter of the quarter circle, that is to say, it equals to 2R, and if DO equals to R, then OE must be also equal to R in order that DE, that is the diameter, will be equal to 2R. Okay, so OE equals to R and R equals to 3 units. Okay, and we will create from the quarter circle a semicircle okay, and we know that DE is the diameter of the semicircle, therefore DE is a straight line. Okay, DE is a straight line, again, DE is the diameter of the semicircle, is a straight line. Okay, DE is the straight line, and we have the rule that the sum of the angles on a straight line is equal to 180 degrees, and if we focus at point O on the straight line DE, the sum of the angles must be equal to 180 degrees. Okay, again, the sum of the angles on a straight line is equal to 180 degrees. So if we focus at point O on the straight line DE, the sum of the angles is equal to 180 degrees. And we know that this angle is a right angle, so we have 90 degrees plus the size of angle EOB must be equal to 180 degrees according to this rule, okay? According to the rule that the sum of the angles on a straight line is equal to 180 degrees. So here we will subtract 90 degrees from this equality, and we will get that the size of angle EOB equals to 180 degrees minus 90 degrees. It equals to 90 degrees. Angle EOB is a right angle. So this angle is a right angle. It equals to 90 degrees. Okay? And therefore, the small triangle EOB is a right triangle. Triangle EOB is a right triangle. And in the right triangle EOB, we know that this angle equals to 2 theta. Therefore, this angle must be equal to 90 degrees minus 2 theta. Okay? Again, in triangle EOB, this angle is 2 theta, so the second angle must complete the sum of those two angles to 90 degrees. So 90 degrees minus 2 theta is actually the size of this angle. Okay? Or we can also say that the sum of the angles in triangle EOB is equal to 180 degrees. So 90 degrees plus 2 theta, 90 degrees plus 2 theta plus the size of angle EOB must be equal to 180 degrees. And if we subtract 90 degrees from this equality, we will get that 2 theta plus angle EOB equals to 180 degrees minus 90 degrees is 90 degrees. And if we subtract from this equality 2 theta, we will get that angle EOB equals to 90 degrees minus 2 theta. Okay, we proved in two different ways that the size of angle EOB is 90 degrees minus 2 theta. In the next step, we will find out the size of angle CDE. We know that the sum of the angles in any triangle equals to 180 degrees. So angle CED plus 90 degrees plus the size of this angle, that is 90 degrees minus 2 theta, must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Okay? Again, the sum of the angles in the right triangle CDE equals to 180 degrees. That is to say, angle CDE plus 90 degrees plus 90 degrees minus 2 theta must be equal to 180 degrees. So in this side of the equation we have 180 degrees, on the other side of the equation we have also 180 degrees, so 180 degrees will get cancelled because we have 180 degrees in both sides of the equation. And what is left after we cancelled 180 degrees? It is left that angle CED minus 2 theta equals to 0. And if we add to this equality 2 theta, we will find out that angle CED equals to 2 theta. Okay, so this angle C, actually it is angle CDE, this angle CDE, angle CDE angle CDE equals to 2 theta. Angle CDE equals to 2 theta. Okay, this angle equals to 2 theta. So we will continue to focus on triangle CDE, the right triangle CDE. So in the right triangle CDE, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CD square plus CE square must be equal to ED square. Okay. Again, in the right triangle CDE, according to the Pythagoras theorem, CD square plus CE square equals to ED square. What is the value of CD? CD equals to 2 units. It is given us the question. So CD square is 2 square. 2 square is 4 plus CE square equals to ED square. What is the size of ED? ED equals to R plus R. ED is the diameter, therefore it equals to 2R. The diameter of any circle equals to 2 times the radius of the circle. So 2 times R is 2 times 3. 2 times 3 is 6. So ED square or DE square is 6 square. 6 square is 36. So we got that 4 plus CE square equals to 36. Here we will subtract 4 from this equality and we will get that CE square equals to 36 minus 4 is 32. Okay, so we found out that CE square equals to 32. We will take a root out of this equality and we will get that CE equals to root of 32. But we know that 32 is 16 times 2. And the root of 16 is 4, so in total we got that CE equals to 4 times root 2. Okay, CE equals to 4 times root 2. Okay. So we know that in the right triangle CDE, tangents 2 theta, tangents 2 theta equals to CE over CD. Again, in the right triangle CDE, tangents 2 theta equals to CE over CD. Okay, tangents 2 theta equals to CE over CD. But we know that CE, we have already found out that CE equals to 4 times root 2, 4 times root 2, and the CD equals to 2. So we found out that tangents 2 theta equals to 4 times root 2 over 2. 4 over 2 is 2. So tangents 2 theta equals to 2 times root 2. So we actually found out that tangents 2 theta equals to 2 times root 2. Okay? Actually, we know that the radius that we want to find out, the radius of the small circle, equals to AB times tangents theta. So we want to find out the value of tangents theta, and we don't have the value of tangents theta, but we have the value of tangents 2 theta. So in order to get the value of tangents theta from tangents 2 theta, we will use a trigonometric identity, and from that trigonometric identity we will get the value of tangents theta. Actually, the trigonometric identity for tangents 2 theta is actually equals to 2 tangents theta over 1 minus tangents square theta. Okay, tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. But we know that tangents 2 theta, we have already found out that tangents 2 theta equals to 2 times root 2. So we will substitute tangents 2 theta in this trigonometric identity by 2 times root 2. So 2 times root 2 equals to 2 times tangents theta over 1 minus tangents square theta. Okay, so in the next step we will define tangents theta as x, and we will find out the value of x. Tangents theta will be equal to x according to our definition. So we'll substitute tangents theta in this equality by x, and we will get that two times root 2 equals to 2 tangents theta. Tangents theta is x, so it is 2x over 1 minus tangents theta squared. Tangents theta is x, so tangent theta square will be equal to x squared. So in total we got that 2 times root 2 equals to 2x over 1 minus x squared. Here in this expression we'll cross multiply this expression by 1 minus x squared, and we will get that 2 times root 2 times 1 minus x squared equals to 2x. Here we will open the brackets, so 2 times root 2 minus 2 times root 2 times x squared equals to 2x. Okay, 2 times root 2 times 1 minus 2 times root 2 x squared equals to 2x. Here we will divide this equality by 2, and we will get that root 2 minus root 2 x squared equals to 2x. In the next step we will add to this equality 2 root x squared, and we will get that root 2 equals to 2 root 2 x squared plus 2x. So here actually we divided this equality by 2, so we got that all the expression here is divided by 2, so 2x over 2 is x. So here we have x. Okay? So in total we got that root 2 equals to root 2 x squared plus x. Here we will subtract root 2 from this equality, and we will get that root 2 x squared plus x minus root 2 equals to 0. So we got here a quadratic equation. The general formula for a quadratic equation is ax squared plus bx plus c equals to 0, when a, b, and c are the coefficients of this quadratic equation, and x is the variable that we want to find out, and we will find out the value of x according to a special formula, that x equals to minus b plus minus root of b squared minus 4 times a times c over 2a, when a, b, and c are the coefficients of the quadratic equation, and x is the variable that we want to find out. So the coefficients of our specific quadratic equation is a equals to root 2 b equals to 1 and c equals to minus root 2. Okay, so we will put the coefficients of our specific quadratic equation in order to find out the value of x. So x will be equal to minus b. B is 1, so minus b is minus 1 plus minus root of b square. B is 1, so b square is 1 square. 1 square is 1 minus 4 times a. 4 times a is 4 times root 2 minus 4 times root 2 times minus root 2 times minus root 2, all divided by 2 times a is 2 times root 2. So in the root we have x equals to minus 1 plus minus root of 1 plus minus and minus is plus, so root 2 times root 2 is 2 and 4 times 2 is 8. So in the brackets we have 1 plus 8, that is 9, so it is root of 9 over 2 times root 2. Okay, and the root of 9 is 3, so we got that x equals to minus 1 plus minus 3 over 2 times root 2. Okay, again x equals to minus 1 plus minus 3 over 2 times root 2. So the first solution for this quadratic equation is x equals to minus 1 plus 3 over 2 times root 2. Minus 1 plus 3 is 2. 2 over 2 times root 2, so it is 2 over 2 is 1, so it is 1 over root 2. So we found out that x equals to 1 over root 2. That is the first solution, but we have also the second solution for x. The second solution for x, that x equals to minus 1 minus 3 over 2 times root 2. Minus 1 minus 3 is minus 4 over 2 times root 2. And minus 4 over 2 is minus 2. We got that it's x equals to minus 2 over root 2, that is less than 0. It is a negative number. But we know that theta is actually inside a right triangle. So if we have a triangle, a right triangle, so this angle is 90 degrees, and here we have angle theta, so angle theta must be less than 90 degrees. Theta is less than 90 degrees, and therefore tangent theta is a positive, is greater than 0. So, and the answer that we got is that x that equals to tangent theta is negative number, is less than 0. So it is impossible because theta must be a positive number, and we got that theta is a negative number. So this is an incorrect answer, and the only answer from the quadratic equation is that x equals to 1 over root 2. X equals to 1 over root 2. And we define x as tangent theta, so tangent theta equals to 1 over root 2. Tangent theta equals to 1 over root 2. So actually the radius of the small circle equals to AB times tangent theta. We have already found out the value of tangent theta. Tangent theta equals to 1 over root 2. So the only thing that is left to find is to find out the value of AB. Okay, again, we found out that the tangent theta equals to 1 over root 2, and we also found out that tangent 2 theta equals to 2 times root 2. Okay, so the only thing that is left to find is to find out the value of AB. Okay, so we focus on the right triangle, triangle BOE. In the right triangle, triangle BOE, tangents 2 theta, tangents 2 theta equals to OE over BO. Again, in the right triangle, this triangle BOE, tangents 2 theta equals to OE over BO. And we know that OE equals to R, that equals to 3 units. So it is 3 over BO, 3 over BO. Tangents 2 theta equals to 3 over BO. But we know that tangents 2 theta equals to 2 times root 2. So we can substitute tangents 2 theta by 2 times root 2. We will get that 2 times root 2 equals to 3 over BO. So here we will multiply this equality by BO, and then we will divide it by 2 times root 2, and we will get that BO equals to 3 over 2 times root 2. Okay, BO equals to 3 over 2 times root 2. Okay, here BO equals to 3 over 2 times root 2. Okay, in the next step we will join together points P and O by a straight line. And we will extend PO until it touches the circle at point M. Okay, so M is the touching point between OP and the circle. So actually OM is the radius of the big circle. It equals to capital R. Or we can say that PO equals to MO minus MP. Again, PO equals to MO minus MP. Okay? PO equals to MO minus MP. But we know that MO is the radius of the semicircle, so it equals to capital R. And MP is the radius of the small circle, it equals to small r. So in total we found out that PO equals to capital R minus small r, but we know it is given us in the question that capital R, or DO that is capital R, equals to 3 units. So we'll substitute capital R by 3. PO equals to 3 minus R. Okay, PO equals to 3 minus R. Okay, and actually line segment O actually line segment OA is tangent to the small circle at point A. Okay, OA is tangent to the small circle. OA is tangent to the small circle, and AP is the radius of the small circle. Again, OA is the tangent of the small circle, and AP is the radius of the small circle. And we have a rule that states that radius and the tangent to the radius and the tangent to the radius are perpendicular to each other. So I will read the rule again. The rule states that radius and the tangent to the radius are perpendicular to each other. Okay, so according to this rule, we have tangent OA and we have radius that are meet at point A. So the tangent to the circle and the radius, according to the rule, are perpendicular to each other. So again, if we have, I will explain again the rule. If we have a circle and we have the radius, this is the radius, and we have tangent to the radius, this is tangent to the radius, so this is the tangent to the radius and this is the radius. The tangent is perpendicular to the radius, that is to say this angle is 90 degrees. The tangent is always perpendicular to the radius, therefore this angle is 90 degrees. So here we have radius and the tangent to the radius, therefore the radius is perpendicular to the tangent, that is to say this angle is a right angle, it equals to 90 degrees. Therefore, triangle POA, triangle PAO, this triangle is a right triangle. That is to say, we can implement the Pythagorean theorem in the right triangle PAO. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the square of the squares of the perpendicular. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PA square plus AO square equals to PO square. Again, triangle PAO is a right triangle because it has angle that equals to 90 degrees. Therefore, we can implement the Pythagorean theorem on the right triangle PAO. According to the Pythagorean theorem, PA square plus AO square equals to PO square. But what is the value of PA? PA actually is the radius of the small circle, that is to say it equals to small r, so PA square is r square plus AO square equals to PO square. We have already found out that PO equals to 3 minus r. So PO square will be equal to 3 minus r square. So in total we got that r square plus AO square equals to 3 minus r square. Here we'll open the brackets and we will get that r square plus AO square equals to 3 minus r squared is 9 plus r squared minus 6r. So here we have r squared in this side of the equality and we have r squared in the other side of the equality, so r squared will get cancelled, and what is left after we cancelled r? After we cancelled r, we left with a all squared equals to 9 plus 9 minus 6r. So we found out that a all squared equals to 9 minus 6r. Here we will take a root out of this equality and we will get that AO equals to the root of 9 minus 6r. We found out the value of AO, and we know that BO equals to 3 over 2 times root 2. BO equals to 3 over 2 times root 2. And what is the size of AB? AB actually equals to AO minus BO. Again, AB equals to AO minus BO. Okay, AB equals to AO minus BO. And we have the value of AO and BO, so we will substitute AO by its value and we will substitute BO by its value. So AB will be equal to AO. AO is the root of 9 minus 6r minus BO. BO is 3 over 2 times root 2. Okay, so we have the value of AB, and we know that the radius of the small circle equals to AB times tangent theta, and we have already found out that tangent theta equals to 1 over root 2. Tangent theta equals to 1 over root 2. So R equals to AB. We will substitute AB by its value. AB equals to root of 9 minus 6R minus 3 over 2 times root 2, and tangent theta equals to 1 over root 2. So in total we got that the radius of the small circle equals to root of 9 minus 6r minus 3 over 2 times root 2 times 1 over root 2. Here we will multiply root 2 this equality. We will multiply by root 2 this equality, and we will get that root 2 times r times root of 9 minus 6r minus 3 over 2 times root 2 root 2 times r root 2 times r equals to 9 here it is equals root 2 times r equals to root of 9 minus 6r minus 3 over 2 times root 2. So here we have root 2 times r. We will add to this equality 3 over 2 times root 2. We will get that root 2 times r plus 3 over 2 times root 2 equals to the root of 9 minus 6r here we will multiply root 2r by 2 times root 2 and then we will divide it by 2 times root 2 in order to have a common factor with this expression. So we will get that root 2r multiplied by 2 times root 2 over 2 times root 2 plus 3 equals to root of 9 minus 6r. So here we have root 2 times root 2 is 2 and 2 times 2 is 4. So here we will have in the numerator 4r plus 3 over 2 times root 2 equals to root of 9 minus 6r. Okay, so here we will square both sides of the equality and we will get that the square of root is the square and the root are cancelled by each other. So here we will have 9 minus 6r and 4r plus 3 square and 2 times root 2 square is 8. So here we will multiply this equality by 8 and we will get that 4r plus 3 square equals to 8 times 9 is 72 minus 48r. Okay, here we will open the brackets in this side of the equation. 4r plus 3 square is 16r square plus 9 plus 4r times 3 is 12r and 12r times 2 is 24r equals to 72 minus 48r. Here we will add to this equality 48r and we will get that 16r square plus 9 and 48 plus 24 is 72 plus 72r equals to 72. Here we will subtract from this equality 72 and we will get that 16r square plus 72r minus 63 equals to 0. Okay, so we got a quadratic equation and the solution to the quadratic equation is x equals to minus b plus minus root of b square minus 4 times ac over 2a that is the solution for a quadratic equation. X is the variable of the quadratic equation, and a, b, and c are the coefficients of the quadratic equation. So in our specific quadratic equation, the variable of our specific quadratic equation is r. So x equals to r, and x equals to r, and we also know that a equals to 16, b equals to 72, and c equals to minus 63. Okay, so we will put the data inside the general solution of a quadratic equation. So x equals to r equals to minus b. B equals to 72, so minus b is minus 72 plus minus root of b square. B equals to 72, so b square is 72 square minus 4 times a is 16, so 4 times 16 is minus 64 times minus 63. All divided by 2a, a is 16, so 2a is 32. Okay, so r equals to minus 72 plus minus 72 square is 5,184 plus 64 times 63 is 4,032 over 32. So r equals to minus 72 plus minus, and 5,184 plus 4,032 is 9,216. So we got that r equals to 72 plus minus root of 9,216 over 32. The root of 9,216 is 96, so I will write it down. R equals to minus 72 plus minus 96 over 32. So the first solution is R equals to minus 72 plus 96 over 32. Minus 72 plus 96 is 24, and 24 over 32 is 3 over 4. Or the radius of the semicircle equals to 3 over 4 units, or 0.75 units. That is the first solution. And we have also the other solution, that the radius of the small circle equals to minus 72 minus 96 over 32. It equals to minus 168 over 32. It equals to minus 5.25. So the radius must be a positive number. Therefore, r equals to minus 5.25 is incorrect because it is a negative number. It is incorrect, so we left only with the answer that the radius of the small circle equals to 3 over 5 units, or 0.75 units. Okay, so the radius of this small circle equals to 3 over 4 units, or 0.75 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. The small circle is inside a quarter circle. We know that chord CD equals to 2 units, DO equals to 3 units, and angle VCE equals to 90 degrees. And we want to find out the radius of the small circle. Okay. First of all, we defined the center of the semicircle as point P. Then we connected together points A and P by a straight line. And then we connected together points P and B by a straight line. And we connected together points P and X by a straight line. Actually, AP is the radius of the small circle, and PX is also the radius of the small circle. Okay. We defined angle ABP as theta, and we know that tangent theta equals to AP over AB. Again, tangent theta equals to AP over AB, but we know that AP is the radius of the small circle, so AP is R, so tangent theta equals to R over AB. We multiply this equality by AB, and we found out that the radius of the small circle equals to AB times tangent theta. So in order to find out the radius of the small circle, we must find out the value of AB and the value of tangent theta. Okay, then we proved that triangle ABP and triangle PBX are congruent to each other, because AP equals to PX equals to R. Both of them are the radiuses of the small circle. PB equals to PB is the common side, and AB equals to BX. AB equals to BX according to two tangents theorem. Two tangents theorem states that the lengths of two tangents from common external point to the circle are equal. So if we have external point of the circle, that is point B, and from point B we draw two tangents to the circle, then AB will be equal to BX. Okay? So in this way we proved that triangle ABPs can go into triangle PBX, and therefore angle ABP equals to angle PBX. So if angle ABP equals to theta, then angle PBX will be also equal to theta. So those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? And then we extended CB and DO until they intersect with each other. The intersection point between CB and DO is at point E. And actually in this way we created two vertex angles. Angle EBO is vertex angle, and the second vertex angle is angle ABC. So angles EBO and ABC are two vertex angles, therefore they are equal to each other. So if angle ABC equals to 2 theta plus theta, that is 2 theta, then angle EBO must be also equal to 2 theta. Okay? So angle ABC equals to angle EBO, and those both two angles are equal to 2 theta. And actually, when two straight lines intersect with each other, they create two pairs of vertex angles. The first pair of vertex angles are 1 and 3, and they are equal to each other, and the second pair of vertex angles are 2 and 4. So angle 2 equals to angle 4 because they are two vertex angles. Okay? Then actually angle BCD, this angle, equals to 90 degrees. It is given us in the question that is a right angle, it equals to 90 degrees, and actually angle BCD is a peripheral angle. And we have a rule that any peripheral angle that equals to 90 degrees must rest on the diameter of the circle. So peripheral angle ECD must rest on the diameter of the circle, that is to say ED is the diameter of the quarter circle. That is to say it equals to 2R. So if DO equals to R, then OE must be also equal to R in order to complete the size of DE to 2R. Because DE is the diameter of the circle, therefore it equals to 2R. Okay? So DE is the diameter of the quarter circle. Then we created from the quarter circle a semicircle, and we know that DE as a diameter is a straight line, and we know that the sum of the angles on a straight line equals to 180 degrees. So if this angle is 90 degrees, the size of this angle, 90 degrees plus the size of this angle must be equal to 180 degrees. So 90 degrees plus angle EOB must be equal to 180 degrees. We subtracted 90 degrees from this equality, and we got that angle EOB equals to 90 degrees. So this angle EOB is a right angle. Therefore triangle BOE is a right angle because it has one angle that equals to 90 degrees. Okay? And triangle EOB is a right triangle, and if in the right triangle, if this angle equals to 2 theta, then this angle must be equal to 90 minus theta. And we know that the sum of the angles in any triangle is equal to 180 degrees, so the size of this angle plus 90 degrees minus 2 theta must be equal to 180 degrees. In triangle CDE, the sum of the angles equals to 180 degrees. So this is the sum of the angles. So from this equality we got that angle angle CDE equals to 2 theta. Okay? And in triangle CDE, the right triangle, triangle CDE, according to the Pythagoras theorem, CD square plus CE square equals to DE square. Again, CD square plus CE square equals to DE square. CD equals to 2, so CD square is 2 square is 2 square is 4, plus CE square equals to DE square. DE is the diameter of the semicircle, and the radius equals to 3, so the diameter is 2 times the radius. Therefore the diameter is 6 units, so DE equals to 6 units, and DE square is 6 square is 36. Okay? And from this equality we got that the value of CE is 4 times root 2. Okay, CE equals to 4 times root 2. And then we know that in triangle CDE, the right Greek triangle CDE, tangents 2 theta equals to CE over CD. In the right triangle CDE, tangents 2 theta equals to CE over CD. But we already found out that C equals to 4 times root 2 and CD equals to 2 units. It is given us in the question. So in total, we found out that tangents 2 theta equals to 2 times root 2. And in order to find out the radius of the small circle, we know that the radius of the small circle equals to AB times tangents theta. So we must find out the value of AB and the value of tangents theta. Actually, we found out the value of tangents 2 theta. We need the value, not the value of tangents 2 theta, but the value of tangents theta. So in order to find out the value of tangents theta from tangents 2 theta, we have trigonometric identity. The trigonometric identity states that the value of tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. Okay, but we have already found out that tangents 2 theta equals to 2 times root 2, so we can substitute tangents 2 theta by 2 times root 2. Okay, we substituted tangents 2 theta by 2 times root 2, and there we have 2 tangents theta over 1 minus tangents square theta. We defined tangents theta as x, and we got, so we substituted tangents theta by x, and we got the equality that 2 times root 2 equals to 2x over 1 minus x squared. So we solved this equality, and we got, from this equality we got a quadratic equation that root 2 times x squared plus x minus root 2 equals to 0. And in this specific quadratic equation, a equals to root 2, b equals to 1, and c equals to minus root 2. And we have, this is the general solution for a quadratic equation, or the solution for x, and x is the variable. And what we need to do here is to substitute the values of a, b, and c that we found in our specific quadratic equation by a, b, and c that we have in this general solution for a quadratic equation. So we substituted a, b, and c by the values that we found for a, b, and c, and we found out that x equals to 1 over root 2, and x is actually equals to tangent theta according to our definition. So actually tangent theta equals to 1 over root 2. So we made halfway, we did half the way for the solution to find out the radius of the small circle, because we found out the value of tangent theta. Tangent theta equals to 1 over root 2, and so the only thing that is left to find is to find out the value of AB. Okay? So we know that tangent theta equals to 1 over root 2, and we have already found out that tangent 2 theta equals to 2 times root 2. So in the right triangle, triangle BOE, we know that tangent 2 theta equals to OE over OB. Okay, tangent 2 theta equals to OE over OB. But OE is the radius of the semicircle. It equals to 3 units. It is given us in the question. OE is 3 and BO is BO. And tangent theta equals to 2 times root 2. So we substituted tangent 2 theta by 2 times root 2. And we found out that BO equals to 3 over 2 times root 2. BO equals to 3 over 2 times root 2. Okay? And then we connected together points O and P by a straight line, and then we extended line segment OP until it touches the circle or the circles at point M. And what is the value of PO? PO equals to MO minus MP. Again, PO equals to MO minus MP. And MO is the radius of the semicircle and MP is the radius of the small circle. So in total, PO equals to capital R minus small r. But we know that capital R equals to 3, so PO equals to 3 minus R. Okay? And we know that here OA is tangent to the circle, AP is the radius of the circle, and AO is tangent to the circle. We know that tangent and radius are always perpendicular to each other, so angle PAO equals to 90 degrees. Therefore, triangle APO is a right triangle. Okay? So we can implement the Pythagorean theorem in the right triangle, triangle POA, according to the Pythagorean theorem. AP square plus AO square equals to PO square. Okay? Or in the right triangle APO, PA square plus AO square equals to PO square. We know that PA equals to small r, AO is AO, and PO equals to 3 minus r. So we open the brackets and in this equality, and we found out from this equality that AO equals to the root of 9 minus 6r. And we have already found out that BO equals to 3 over 2 times root 2. So what is the value of AB? AB equals to AO minus BO. Again, AB equals to AO minus BO. AB equals to AO minus BO. and we have already have the values of AO and BO, so we substituted AO and BO by their values. So AB equals to root of 9 minus 6R minus 3 over 2 times root 2, and we have already found out that tangent theta equals to 1 over root 2, and R, the radius of the small circle, equals to AB times tangent theta. We have here the value of AB equals to this expression, and we know that tangent theta equals to 1 over root 2. So we can substitute AB by its value, and we can substitute tangent theta by 1 over root 2 in this equality, and we got that R equals to this expression. So we solve this equality, and we got to a quadratic equation. That 6 times R squared plus 72R minus 63 equals to 0. We solve this quadratic equation. We add two solutions to this quadratic equation. One of the solution is incorrect, and we left only with the solution that the radius of the small circle equals to 0.75 units or 3 over 4 units. Again, the radius of this small circle equals to 3 over 4 units, or the radius of this small circle equals to 0.75 units. Okay? Thank you very much.